Hello everyone and welcome to yet another recreation programming session with Mr. Azozin. So we continue developing our programming language, and I think the time has come to implement pointers. How about that? So the language we're developing is a B programming language. It's basically predecessor to C. So this is what Ken Thompson and Dennis Ritchie created before C. Then they saw a lot of mistakes in this language and they fixed them in the next iteration of this language that they called C. So the thing about B is that it doesn't really have any types, like at all. It just doesn't have any types. Like you can say that it has one type, which is a word, which is like an integer, and the size of that word is the size of the machine for which you're programming. At the time it was PDP-11, as you can see, it's for PDP-11, and as far as I know, PDP-11 was actually a 16-bit machine. We implement a language for x86-64, which is 64-bit. We also have a platform for ARM. It's not fully finished, but nothing is really finished in this particular compiler yet. Right, so and essentially how you implement a pointer is you have a variable, right? You have some number in that variable, and then you use a usual dereferencing syntax like in C, which comes from B, obviously, and it basically gets treated as a dereference of the pointer. Right, you just have a number, you try to dereference that number, and the compiler treats that as a pointer, and it tries to read from that specific address. That's it. So, and then you can try to reference something, right? So we use at operation, and in that case, it will try to take address of that thing. So very easy, very straightforward. We can try to implement like a simple example that will demonstrate this kind of thing. So let's actually create pointer B. Right, so, and this is how function look in B, right? So again, no type, no anything, everything is an integer, everything is a number. And let's actually create something like, I don't know, P, right? And in P, you can put something like 69 for 20. And then you can literally just dereference this entire thing and try to write something into that. Right, so, and it will try to basically write into that specific address. It doesn't do that right now because we haven't implemented that yet, but you know, hypothetically. So, which also means that we can do things like this. We can do malloc. We can allocate, for example, 8 bytes, which is the size of the word. And obviously we have to say that we are going to be declaring this thing as an external symbol. Otherwise, it won't be able to call it. Right. And then we can just write some stuff in there. In fact, we can allocate like maybe an array. We haven't implemented arrays yet, but we already can kind of allocate them on a heap if we had pointers, right? So, and on top of that, you should be able to perform like pointer arithmetic or something. So you can kind of have arrays, right? You can kind of have arrays and stuff like that. So as far as I know, just doing that will already work, right? So we can try to maybe print that pointer. We won't be able to dereference it, but we'll be able to see what's the value of the pointer, because pointer is just a number. It's basically an address in the memory, right? So let's actually try to print this entire thing, and basically P means that print it as a pointer. Printf is actually capable of recognizing pointers, and it will print them like in hexadecimal format, right? So to signify that it is a pointer, in fact, and not just a random integer. So let's actually rebuild the entire thing, and I'm going to try to call this compiler on pointer B, and it doesn't compile because it doesn't know where is printf. Let's put printf in here, right? So it's external symbol, and it compiles. Right, let's try to run this entire thing. And it actually, yeah, I should put // in here. There you go. And it printed an address. So there is something by that address, but we can't really read it. Right, so let's try to maybe write something in here like 69 and then try to read from that address. So so this is going to be our sort of like a test example, right? So if we implement everything correctly, this specific example should print 69 as a sort of like a checksum. Okay, so I forgot. Oh, yeah, so it's not implemented yet, right? It's not implemented yet, but I did in fact forget a semicolon. Right, so it doesn't expect like a star in here. So let's go ahead and just start implementing from the syntactical point of view, right? So how it's going to look that from the syntactical point of view. So as far as I know, this is just a primary expression. Right, so I'm going to try to find compile primary expression. So this is where we're compiling this primary expression, right? And now I'm looking at what this expression starts from. So it can start with open parent, it can start with exclamation marks, and if it starts with star as I64, we have to compile it slightly differently. So first of all, we have to compile sort of like the inner expression, right? So it starts with star and then comes some other primary expression. So we actually have to like parse the next primary expression. And here's an interesting thing. So compile primary expression actually returns you a pair, right? It returns you, first of all, an argument, which describes where is the value of this expression stored. Right, where is the value of this expression stored? So here we have a compiler that doesn't really build AST. It doesn't really build AST. It just compiles the source code and emits assembly and then tells you where to get that value that it just compiled. Right, and then it returns a Boolean. And Boolean actually signifies whether it's an L value or R value. This is quite important. This is quite important. So essentially, L value is any expression that you can put on the left, and R value is any expression that you can put on the right. So not any R value can be L value, right? For instance, like just a number constant cannot be L value. You can assign the number constant to a variable, but you can't assign anything to the constant. Right, something like that. So, and essentially, initially we implemented this L value and R value detection as AST, right? So I spent some time actually parsing AST because I thought that, all right, so as I parse this expression, as I compile this expression, I don't really know whether it's a left value or right value up until I encounter equals, right? And because of that, I thought I need to sort of like collect first the structure of this expression, and when I encounter equals, only then I should start the compilation. But then I realized that during compiling any expression, I can kind of keep track, can I interpret this expression as an L value or not? And if at some point I encounter some elements that make it impossible to think of this expression as an L value, I can just, signal that additional information to the to whoever called this parser through this additional return value. And that additional return value basically tells whoever calls this function, can you interpret this thing as an L value or not? Right, and because of that, I don't really need the AST anymore, right? So it's not really needed. And this is kind of important because this is something that we're going to be using here, right? So because you can only dereference R values, right? So maybe actually it can be any value, right? So it's just like any value. But at some point we'll need that distinction. Okay, so for now, let's actually ignore this bit, but I feel like we'll need it at some point. So anyways, okay, so we compile the inner expression and now we need to dereference it somehow. The question is how exactly we're going to be dereferencing this entire thing. This is rather interesting because we essentially store different values of the expression in something that is called argument, right? An argument can be an autovar. It's basically a variable that is stored on the stack, right, and deallocated automatically when you exit the function. It could be a literal, right, so just like a regular literal that is not stored anywhere and it's usually an immediate value. Or it could be a data offset. It's essentially an address of a string within the data section, right? So at the compile time, you don't really know where the data section is located, but what you know is that there are strings in there, and you know an offset from the beginning of that data section to a particular string. So this is what you know. I have a feeling when you dereference something, we need to introduce a new kind of argument, which basically tells you like that this thing is an address in memory, right? It tells you that this thing is an address in memory somehow. But where is that address in memory is going to be stored? We can actually kind of store it in an automatic variable, sure. We can store it in an automatic variable, but on top of that, we can't use autovar because it's interpreted slightly differently. So I feel like maybe we should introduce like another thing in here, which is going to be a reference, and it's going to be an index of automatic variable. But when you encounter this thing, you basically interpret that the content of that specific automatic variable is an address in memory and not just a regular usual thing. So like when you try to read from this argument, you're not just reading a value from automatic variable, you're reading a value from automatic variable, and then you do another read to get a value out of that or something like this. So yeah, that's how I see that. I think this is what we have to do in here. So this not allowed? I think in B, this kind of stuff should be allowed, in my opinion. Right, so I think it should be allowed. So we're getting some subs. Let me actually quickly acknowledge them. So thank you so much, XV, for the Prime with the message Tsodimpok indeed. Azora Kimura, thank you so much for 29 months with the message Midnight Zuzin stream. My time zone, who needs sleep? I'm really sorry if that actually makes you not sleep, right? So, but my sleeping schedule is also fucked up, so I stream whenever it is convenient for me. Would LLVM handle all that, or do you still have to manage stuff manually? I don't remember how LLVM works, honestly. I honestly do not remember how it works. Okay, let's actually try to allocate an automatic variable, right? So we basically compiled an inner expression behind the one that we're trying to dereference, right? So, and basically this argument stores something, right? So it stores the address. So then we allocate another automatic variable, whatever that is, and I suppose what we have to do, we have to store this argument which stores the address into that new automatic variable to ensure that that address is stored in automatic variable, because then we're going to use the index of that variable for the ref argument. So that's kind of important. So let's actually do di append. We're appending into the function body. We're appending into the function body, so like this. And let's just like literally assign, right? Literally assign to the result. Might as well maybe call it an index, because if you take a look at OP assign, right, it's actually auto assign. Maybe at some point I should rename it to just assign. So this is an index. We're assigning this argument to index. Okay, so essentially when we dereference something, we compile that argument, that expression, then we allocate an automatic variable, always allocate automatic variable, and just store this compiled expression into that automatic variable. That way we want to ensure that argument is inside of an automatic variable, right? Because this argument might be just a literal, right? It might be just a literal, it might be something else, right? So we got this expression that we want to interpret as a pointer in an automatic variable, and now we're able to say, okay, now interpret this expression in that automatic variable as a ref. So that's a new kind of argument in here. That's what we have in here, and we have to return it actually. So, and yeah, by the way, you should be able to assign to this dereferenced expression. So because of that, it is in fact an L value, right? So things like not some sort of expression is definitely not an L value. You can't assign anything to that. For example, you have some sort of a condition and you said not that condition. You can't assign to that. You can't assign anything to that. But if instead of not you have star, you can in fact assign something to that, right? So that kind of works out. So yeah, I guess that's basically everything for the syntactic compilation, right? So, but then we need to go through all the places where we do argument handling and maybe stub some things or even implement some things. So let's actually see how the compiler is going to react to all of this. So make -b. All right, so what do we have in here? Okay, so we are currently in gas AR64, right? So this is ARM, and here's the function that loads the argument in a particular register on ARM, on ARch64, right? So in here, what we have auto variable, right? So it's on the stack, it just loads that variable by that index into the register. If it's a literal, it just loads the literal. Loading literals in Arch is, as you can see, it's very complicated. We did that on the stream, right? So if they are bigger than 4 kilobytes or whatever, I don't remember, like 16 bits, you have to split them in chunks and then assemble them chunk by chunk. So it's a huge pain in the ass, and that's the price of RISC architecture, I suppose. And here's the data offset. Data offset is also kind of anal, right? So because again, the instructions are very small, 16 bits, right? So you have to piece together like big values and stuff like that. So now we have to introduce reference, right? So now we have references in here, and I'm not sure if I want to deal with ARM right now. So I'm going to just say, okay, I'll implement that later, right? Next one. Next one. Okay, this one is a little bit more interesting. This is a FOSDEM x86-64, right? So this is the architecture that we're currently in, and I think I want to implement this one, right? So it's going to be arc auto, not really autovar ref, future you problem, exactly. But I mean, maybe somebody can submit some sort of a pull request, right? So I don't know. Okay, so here's an index, right? And all right, we loaded the value of that automatic variable into some sort of a register. Like, which register do we want to save it? Right, we can actually save it literally into the same register. I think we should be able to do that. But then we have to read from the context of that thing. Yeah, so we have to read, do another read, because that specific variable contains an address that we have to load. So we do kind of a double read in here. So I wonder if you can do something like, so let's do it like this. It's going to be for move as, and just dereference it one more time. Is that a thing you can do? I feel like it might depend on the specific register, because not all registers in x86-64 support this kind of thing. So, but we'll see, we'll see. So what else do we have in here? Okay, so is be append. So this is okay. This is kind of weird. Since I put semicolon in here, the result of this branch is void, but I didn't put this thing in here. So, and the result of this append is how many characters it appended to the string builder. So these branches have result integer, but this branch has result void. So, and to fix that, you have to remove that semicolon. So welcome to Rust syntax. Welcome to Rust syntax. It makes sense. Trust me, it makes sense. Okay, so here is the architecture for intermediate representation, right? So, and I think it's kind of easy to implement this one, right? So because it just prints things, we can just do ref. So this is going to be ZU, and this is the index like this. Can I do something like align? Look at that. Implicit return is evil. It's not even implicit return. It's more like expression-based language. So here's the thing. The syntax of Rust makes sense in the context of a camel. All right, and this is because the original implementation of Rust was in a camel, in fact. But what's interesting, a camel is semantically a different language. Like everything syntactically in a camel makes sense for a camel, but then they're trying to put it on Rust, which is more like a C++, and it just looks weird. It just looks weird and causes a lot of confusion and stuff like that. So I don't know. I don't know. I do not understand that, but so here is the JavaScript. We haven't given too much love to the JavaScript architecture lately, right? So it doesn't even support jumps yet, and this is because JavaScript doesn't have go-tos. By the way, does anybody know, like, can I just have arbitrary go-tos in JavaScript? I briefly Googled it up, and I didn't find anything. JavaScript go-to. You can have labels, yeah. So there's a label statement, but I think you can just break out. Yeah, so it's for breaking out of the loop, but it's not for jumping around in arbitrary places. So in our intermediate representation kind of implies that you can jump around in arbitrary places, and that is not that easy to translate to JavaScript. what's interesting is that some of the intermediate representations kind of solve that by not having, instruction that jumps around arbitrarily. They have entire blocks. They introduce a notion of block out of which you can branch out. Right, so kind of similar to WASM and stuff like that. I have a feeling that we'll have to do the same, right? So if you want to support the maximum amount of different architectures, we need to be able to account for architectures that simply do not allow jumping around in arbitrary places, right? So things like JavaScript and even WASM. WASM does not allow you to jump around in arbitrary places. It has so-called loop and block, right? And the only way for you to jump somewhere, right, you branch out of the loop or you branch out of the block. Maybe it's a giant switch statement and use continue to jump. I'll probably have to think about it. Yeah, so you can use continuous in switch. Wait, you can use continuous in switch. How does it even fucking work? Switch continue. C. Is that a JavaScript thing or is that a C thing? Using continuous switch statements. Wait, I'm programming for almost 20 years. I never heard about this shit before. It's fine. The continuous statement relates to the enclosed. Okay, it's probably JS thing. I mean, for a loop with a giant switch in JS. I need to think how to do that, right? So I can't really obviously like immediately see how to do that. So, but I'll think about that. But anyways, so here's the generate arg, and for now, so this is a reference, and we also need to think how we're going to be doing pointers in JavaScript, right? So maybe we can just basically operate on like uint32 array, right? So this is going to be our memory in which we're doing things at some point. I don't really know. But as of right now, it is just easier to say, I don't know, future me problem. So let's go. So what else do we have in here? Okay, so when I'm assigning things, this one is interesting. Okay, so I have a assign and plus assign. Assign and plus assign. So when I'm assigning to an automatic variable, I just do add, and that's totally fine. But if I'm assigning to auto something like a ref, so what do I even have to do? That's a very interesting thing, because I can't do this kind of stuff, because this thing contains a pointer. So adding together the point is not going to work. I think for now, for the assign plus, and assign plus is essentially this operation. So where is that? This operation. It's essentially this operation. By the way, so originally in B, this operation was something like this. And I think I posted that on, I posted that on Twitter, right? So, and I was wondering, like, why is it like that? And people on Twitter told me that it's like when you do something like this, it's very easy to make this kind of mistake, right? So, and apparently at some point they just like change it like this. And we are using the C notation because I'm using C lexer, right? So, but maybe at some point I'm gonna actually keep it, historically correct, and I will implement my own custom lexer that, imitates the B lexer. Yeah, that's syntactically ambiguous. Yeah. But at the same time, it's actually rather easy to refactor things. My original code looks like this, right? And look how freaking easy it is to refactor like this. Like, isn't that cool? It's so freaking cool. Just like remove that and it kind of makes sense, but at the same time it creates ambiguity, so it's kind of annoying and stuff like that. So it's understandable. It's understandable. All right. So I think for now I want to maybe say I don't really care about this kind of thing because I don't do plus equals for the pointers right now, at least for the dereference pointers. So, and the only thing that we're going to have in here is probably for the assignment, and assignment is rather interesting, right? So we have arg ref. So this is just an assignment. And here we just assign a variable, right? So it's an auto assign. It takes an argument, right, and assigns it to the variable. But now the variable doesn't contain the value. It contains a reference. It contains a reference. Because of that, I feel like we must introduce a new intermediate representation instruction, store. See what I mean? So essentially, instead of assigning a variable, it interprets it as, okay, this variable contains an address into which you want to store this value. So it performs a one dereferencing. So this requires like additional operation. And because of that, I feel it makes sense to actually like rename this operation to assign. So you have assign and you have store. Right, assign modifies this automatic intermediate variables, and store performs actual sort of write to the variable. And because of that, at some point, I think automatic variables will become sort of like registers, right? They're not necessarily have to be stored on the stack. They could become registers, but not for now, not for now. Okay, so let's actually try to introduce a new thing in here. So it's going to be assign, or maybe actually just do store like this, and that means that will trigger errors in all of the backends in here, x86, Arch, and JavaScript and stuff like that. All right, so what do we have in here? So we are currently in ARM, right? So let's go ahead and find assign, OP, store. We're not going to be implementing that for ARM right now. So stubbing a lot of things, just stubbing a lot of things, that's totally fine. So x86, 64, okay. So where is the autos? Here it is, okay. So store, here's the index, and here's the arg. Okay, that's very interesting. So I'm gonna actually keep it to doing here, but we'll get back to that after I finished stubbing things, right? Because I'm gonna try to compile our example, and hopefully it will crash in here, right? So, and then we're gonna implement this entire thing. So for now, I'm gonna actually put dot in here. What else do we have in here? So this is intermediate presentation. So for the intermediate presentation, I suppose I can implement the usual rendering. So might as well steal this rendering from here, right? So this is just an index, this is an argument, but it's simply store. And since B programming language has only numbers of the size word, we don't really need different sizes of store, I think. Do we need different sizes of store? I don't think we need different sizes of store. You can only perform stores and loads of the size of the word. And by the way, because of that, to be able to write cross-platform B code, we should be able to know, at least at compile time, somehow the size of the word, right? Especially I'm using malloc, right? Especially if I'm using malloc, like how do I know, right? How, like, what's the size of the word, right? I should be able to do things like where is the thing, like this, something like this. And then if I want to get the next element in here, I should be able to do things like this. I definitely should be able to do this kind of stuff, right? Because changing the size of the word changes the size of the reads and writes. So having this additional extra constant is kind of important. I don't think I create variable autovar, but I mean, I want the same piece of code to compile on different platforms with different sizes of word and work kind of similarly. So on x86 you can do Leo. Yeah, I know. Anyways, let me see. So we got this kind of stuff. All right. So what is that? This is a JavaScript. So for the JavaScript, we don't really know how exactly to implement all of this kind of stuff. So what is this store? I'm going to stop this entire thing. So this is going to be like that. And what else? Okay, so it compiles. That's pretty cool. Now, can I just try to do something like this? So this is a pointer. Please compile. Error. Oh, yeah, so we should not do that. We don't have a word yet. Panic, not implemented yet. Okay, so we're trying to store some sort of an argument somewhere. All right, that's pretty cool. Let me see. So this is the index. And that index contains the address into, like, yeah, so it's an automatic variable. It is, in fact, an automatic variable. We also have an arg, right? And the first thing we do, I think we need to load the arg into the register. We need to load the value that we are about to write somewhere in the memory. So here's the arg. And I suppose I kind of want to keep this address in a register rex. So the register into which I'm going to be loading the argument is going to be, let's say, rbx, right? So this is going to be rbx, and we're generating that into the string builder, like so. So how I'm gonna load this thing? So I think I can just grab this stuff. All right, so this one is gonna be Rex, and I'm basically taking the address from this automatic variable into Rex. Okay, and then I have to perform a single move. Append output, so something like this, move. So we are performing Rex RBX. So something like this. So that kind of implies like first getting the value out of that and then dereferencing that specific value and like saving it there. Hopefully it will automatically know the size of the read because of this register, but we'll see. All right, that is it, I think. That is it. So, all right, so it didn't like something. So move RSI. Ooh, undefined. What the fuck is this? How did we get to this point? What the fuck? Yep. It was trying to print some things. Okay. Didn't expect that. Okay, so can I just like comment out this thing? Yeah, that wasn't expected. It generated something, but we kind of need this thing. And that doesn't really freaking work. I don't really know. Let me take a look at what kind of changes did we do in here. So when I'm reading from there, so this is a mutable function body. It's really saying yeah, exactly. It's saying So this is what you get for using crust. So in here, did I put any C's anywhere properly? I think I did, right? So, and yeah, look at that. So this is first argument, and this is sort of like a second argument. And I think I know where that happened. And that happened somewhere here. I see. So I forgot to put reg in here the second time. Yeah, I found it. All right. So, and it compiles, right? Look at that. So this is, yeah, so it just does the double dereferencing. And it's totally fine to do this kind of stuff. As you can see, the assembler actually assembled this entire thing. And if everything is correct, right, so the final result is going to be 69 because we're allocating some memory with a malloc. Right, then we storing some value by that memory, and then we're reading it back and printing with printf. Right, so this is sort of like a checksum. Let's actually try to run this entire thing. And it printed 45 because we asked to print it as a hexadecimal, as a pointer, right? So if we do something like this, it is in fact 69. Right, so here's an interesting thing. We allocated 10 words in here, which means we should be able to do things like 8, for example, for 20, or plus 16, something like this. So we should be able to do this kind of thing. Maybe we then should be able to iterate with the loop, right? So we just like stored some stuff in here. And now, okay, so I'm gonna do 0, then while I is less than 0, right? While I is less than 0. In fact, we can just like assign P in here. It's gonna be better like this. Then I'm gonna do P plus I multiplied by 8. I'm gonna dereference this entire thing and I'm gonna print it, right? So I'm just like iterating it essentially. dn like this, and then here I need to do I plus 1. We don't really have plus plus yet. All right, so if I try to run this entire thing, and did it run? It didn't freaking run because, oh, it's 0. It has to be 3. Yeah, there we go. Works. We can effectively have arrays now, chat. Isn't that cool? That's actually pretty cool. That's kind of an absolute churning moment. So I don't have a syntax for arrays yet, but I can already have arrays just because I have pointers. And what's interesting is that I don't need ampersand, right? So ampersand is kind of needed for passing values by a pointer. but just for having arrays, dereferencing is more than enough. It is in fact more than enough. Yeah, so I can just like, I can implement something interesting. For example, rule 110. Yeah, I couldn't implement rule 110 because I didn't have arrays, right? So I thought I'm going to postpone that so until I implement arrays. But just having dereferencing is enough because I can allocate arrays on a heap. So does B not have a pointer arithmetic? Well, I mean, does it look like it to you? The thing is, it doesn't have types. Like, how does it know like how much to offset? Though, if I interpret P as a vector, I expect that all of the pointer arithmetic is going to be kind of by the size of the word because there's only word in there. But then if I do this kind of stuff, it's going to be all bytes. That is very interesting. So by using arrays, or as they call them, vectors, you are effectively doing pointer arithmetic by the size of the word. But if you do it like that, you're doing it by a byte, right? So you kind of have like a fine control over that. That's very interesting, actually. And by the way, because of that, for doing pointer arithmetics, you don't need this magical word. You don't need to know the size of the word because just purely by doing this kind of stuff, you already kind of offset by the word. And that is already more cross-platform than doing something like this multiplied by 8 or multiplied by 2, depending on which platform you're on. But you still kind of need the size of the word if you want to allocate some stuff. We need to have like a malloc specifically for B that accepts the amount of words instead of the amount of bytes or something like that. Like, does the standard library of B that is documented in here have anything like that? So let me see. So here's the library functions. You can change directory. You can do chmod, chown, create files, open files. That's basically POSIX stuff. You can do a lot of POSIX stuff. Type modes and some. This all of that is for PDP. Right, I didn't think so. I actually don't think you can allocate anything. Yeah, maybe maybe dynamic memory allocations was not Balloc. It was Balloc. Oh, he's just memeing around. Yeah, so maybe dynamic memory allocations on machine like PDP-11 was not a big thing at the time. Yeah, I kind of vaguely remember that even dynamic arrays at some point was just like this new thing that people thought is just kind of like a fad and everyone will go back to static arrays or something like that. Yeah, I feel like dynamic memory allocation at the time of PDP-11 was not a big thing. So because of that, it doesn't have a malloc. No structs, no pointers, do structs or array of structs. Yeah, so there's no structs, but I mean, you can just manipulate pointers if you need to. You can just manipulate pointers. You can simulate structs. The same way you do in assembly, essentially, right? So it's a higher level assembly. It is basically a higher level assembly. All right, so let me see, what else can we do in here? Can I don't know. Can I do some interesting thing? For example, iterate. So I'm gonna call it it, and in here is gonna be it p, and then it's kind of interesting because I want to have like a way to check where is the end. Okay, so what if I have n and this is 10 and I'm gonna put n in here. Okay, so then I assign this thing like that. Maybe we also can have like a word, size of the word. So this is how many things we want to have in here, and this is the size of the word, and this is how much we want to allocate. And p is the base, sort of like a base pointer. Might as well actually call it base. The base. Right, so this is the base. Then we're starting from the base, and while it is less than the base plus n multiplied by word, right? Which is, again, we don't have any optimizations, which means this particular like expression is going to be evaluated on each iteration. Because of that, maybe it makes sense to actually have something like end, right? So we have base end. Let's actually do simp mod so we can see like keyword highlighting and stuff like that. So an AND is essentially base plus n and 4. That didn't be. So we do not approve of racism, but I mean, it's the amount of words. It's the amount of words. So now, what do we have? Right. So, and we're iterating this entire thing. So it, and how can we do that? We need some sort of an iterator. And since we do need an iterator, I feel like I have a strange feeling that, yeah, so having a base in here like that is not really important. So what we can do is essentially I is less than n, right? So we don't need the end in here. So this is that, and then plus word plus 1. Yeah, something like this. This is what I want to do. Is this Doom Dark Ages? Yes, it is in fact Doom Dark Ages. So this is that, and afterwards we're gonna start iterating from 0 up until 10, n, but it base. So we are kind of iterating it like this. And we're doing it like that. I'm just thinking what's the best way to do that, honestly. It's kind of annoying that I have to have 2 variables to iterate it like that. But it is what it is. Right, so yeah. Base is not properly assigned. Okay, so so we have this kind of stuff. What do you think? What do you think? So we can now extend this kind of stuff to 20, right? And maybe to even 30. So, and that actually allocates, you know, this amount of words. That actually allocates all of that stuff. And in fact, what I want to do in here is maybe implement rule 110. Right, so I want to implement rule 110 and something like this. Yeah, so I initialize all of that with 0, but if I want to print the whole thing, I'll have to print it like that. Yeah. So, and then I'll have to sort of iterate and so on and so forth. You can even read the entire file with that. Yes, I can. That's actually kind of cool. So now I can read files. So like this language doesn't support much. But it already can do lots just by having these simple operations and stuff like that. So that's pretty cool. You know what? I really want to implement that. I really want to implement this thing. So, but I also want to make a small break because I need a cup of tea. So I've been already streaming for 1 hour, right? So I think it's fair to say that it is time for a small break. Yep, we are back. So let's go ahead and try to maybe implement some Scheiße, meine Freunde. So how are we gonna go about that? I suppose, so we initialize this whole thing with 0. I wonder, can we just use memset? I think we should be able to just use memset. Memset base 0 and then the size of the whole thing. Like so. Yeah, so should be actually fine, and then we should be able to do this kind of thing. So if I try to run the whole stuff, right, it is 0, 0, 0. Okay, I wonder if I can maybe, depending on whether it's 1 or 0, just like print different things. So if, for instance, this is, you know, that, if it's something, I'm going to print maybe a hash, right? So I'm just printing hash. Otherwise, well, I mean, brain damage from the Rust happens. And this one is going to be just like something like dot. Right, so something like dot. I think that's a really good way to do that. And we don't have if, bro. What the fuck? how am I supposed to? How am I supposed to even do this kind of thing, right? So, yeah, like we need to implement if. Hold on a minute. I'm learning Rust. It will give me brain damage. Well, I mean, if you program in too many languages, they're all gonna give you brain damage. They're all gonna give you brain damage. So it's just like, you know, you got used to one way of doing things and then you switch it and now you have to do that differently and stuff like that. Okay, so I wonder what's the easiest way to do that. That's really fucking annoying. I don't have enough constructions. Do I go ahead and try to implement if right now? Because I feel like it could be like a potential... It could be a potential rabbit hole that I don't want to go into. I really don't want to go into. So let me see. So we have things like while. So how much time do I have? I think I have enough time, right? So maybe I can afford this specific rabbit hole, because look at that. Here's the while loop. This is how, you know, easy it was to implement a while loop, right? So maybe it is going to be easy to implement like a if loop, just if construction. So essentially, what do we have? If you have an ID and this entire thing starts with if, like so, you have to do something. First of all, you have to compile the expression, right? So here we have something like this. So we already passed the if keyword. Then we should encounter open parent, and obviously at the end somewhere here we should encounter like a closing parent. So afterwards we have to compile the expression itself, right? So we have to compile the expression itself, and this is arg. And essentially then, depending on whether it's true or false, we have to jump somewhere, right? We essentially have to jump somewhere. So interestingly, in while loop, by the way, look at that. Before compiling an expression, we save the amount of automatic variables and we restore it. So this is all kind of needed for automatically deallocating them. So essentially, you have while loop, right? And you have an expression in here. This expression may be kind of big. And as we compile this big expression, we're allocating like different intermediate automatic variables. That's what we're doing in here. But as soon as we kind of go past this expression, all of the automatic variables that we allocated in here and use for intermediate stuff, they're not really needed anymore. And they can be reused down there in more different statements, right? Because each statement could be an expression, right? So expressions could be statements. And because of that, we kind of like save how many automatic variables we have already here, compile the expression, right, and then restore whatever we had before we compiled the expression, basically deallocating all of these automatic variables. Does it make sense? Right, so that's basically what's going on in here. So it allows us to then reuse different, you know, automatic variables. And automatic variables are kind of like registers, but right now we store them on a stack because it's easier. But in the future, I feel like some of the automatic variables could be stored in registers. Yeah. In fact, we can already kind of do that, can't we? We can already kind of do that. We can just like say, okay, so some of the chunk of the automatic variables, just store them in registers that don't get clobbered or something like that. We can already kind of do that. So yeah, makes sense. But I'm not going to be doing it right now. So anyways, maybe right now, what I need to do is just like do something like that, right? So I save allocated. Let's not save it, right? So I think it adds a little bit too much mental effort for me to think about allocating, deallocating variables. Let's just do the usual thing. So we got the value of the expression, right? So we got the value of the expression, and now I have to append some instruction in here, right? So into the body. C function body. So where is the func body? And I think we have to do jump if not. So we're going to be jumping into else. We're going to be jumping into else if this argument is actually not a correct argument. Yeah. So that's what we're going to be doing in here. So this is that. All right, but we don't really know where we have to jump. That's the thing. We don't really know where we have to jump. We then have to kind of save this specific place and then back patch it later. Okay, so we've got this kind of thing, and after this specific condition, we have to compile a statement. Do we? Yeah, so we just do compile statement, and it's going to be L input path, this kind of thing. Right, so here is the condition. Here we're checking condition, then compiling statement. Right, so simply compiling statement. And after that, we have to expect else. We have to actually check. So do we have else or do we not have else? We can, for now, let's actually say that we're always going to have else. I think that's going to be easier. This is a recursive descent, yes. So this is a recursive descent. So, yeah. We can do something like this. Get and expect collects, a very specific collects, and that specific collects is going to be ID. Right, so as of right now, I think we don't really have expect specific collects ID. We don't really have such operation, even though I feel like it would be kind of nice, right? So you can expect a specific collects, but then you can expect a specific ID, a specific keyword, right? Because our Alexa right now doesn't really distinguish keywords. So things like if, whiles, and stuff like that, they're considered basically IDs. So because of that, I feel like what we have to do, we have to introduce something like expect collects ID, right? So expect collects ID. And in here, something like this. Here we're not expecting a specific, token. We're expecting a specific name, or maybe ID. Let's call it ID. So it's going to be const char, and obviously it may fail. So it's going to be option like so. All right. So we're going to be expecting collects in here. So something like that. And it's going to be collects ID. So this is collects. And after we got this collects, we have to check whether it's equal to this specific ID. So it's a L, it's a string, and strcmp, this is strcmp ID, and if it's not equal to 0, this is where we report an error. Right, so this one is going to be some, this one become none, maybe even return explicitly, and we have to throw diagnostics. So this is how we throw diagnostics. So this is where first char, this is where it occurred. Expected, we can say that we expected ID, but got something else, got specifically this thing. All right, so maybe it makes sense to actually wrap them with backticks. Right, so now we have expect collects. But also I want to have a variant that gets an expect collects. So essentially these functions just check whether the token that Lexa fetched is what we expect, but they don't fetch it. Right, they don't fetch it. You have to explicitly fetch it. But sometimes it's kind of like you may forget this kind of operation. So I usually have this helper function that says get and expect. Right, so it fetches and simultaneously checks whether it's what you expect. So, but sometimes you want to do this operation separately, right? So it's kind of like have several variants of functions that do these kind of things. All right, so I'm going to have this kind of stuff, and then I can do collects ID, and obviously the ID in here is this, so it's going to be const char, and it just gets this entire thing and then forwards to expect collects ID. So that's what's going on here. So this is the Lexa, and this is that, and then yeah, it just returns option this one. It may not fail. All right, so this is what we get. So let me try to compile this entire thing. So, and it doesn't compile somewhere here, surprisingly, because I put double if in here. Yeah, so it's kind of funny. So what do you want from me now? So here's the strcmp mismatched type. Doesn't like something about the type. So let's actually put a to do here at the bottom. So when it reaches it, it actually fails with panic. Okay, so all of that stuff is unused. Maybe I should just for now mark it as public so Rust shuts up, right, because I don't really plan to use them. Okay, so that fails now. Right, what I want to do in here is I want to say expect lex ID, a specific ID. So we're expecting specifically else, right? So we're hard expecting it. So you always have to provide it. We're going to make it optional later, right? So I'm going to do make else optional, because for now it's just like easier for me to implement both of them. If you don't need else, you can just make it empty, right? So so now this is gonna be this kind of thing. And so this is else, and here's the fun part. You have to just imagine how it all works. You just have to imagine how it all works. You have if condition, then else, and then you have basically then branch, and then else branch. So essentially the point of condition somewhere here, if it's false, to jump into else, right? So you kind of have to, I wonder if I can actually sort of denote it like that. Right, so that's kind of your whole point. Like you jump in here. But then, if you don't jump in there, in the then branch, you have to jump over, right? So this jump should jump over here, right? So it has to skip else somehow. So here's the condition, it jumps here and it just skips there. Else, when it reaches the end, I suppose it just doesn't do anything. So basically we have two jumps, one conditional one that jumps to the else and one unconditional one that always jumps over the else. So that's basically what we have to have in here. So let me think how we're gonna do that. So this is just this thing, and I will have to do di append at the end of this thing. Right, so this is gonna be C func body op, just the jump, just always jump, and it's gonna be somewhere there over this entire stuff. Okay, yeah, that looks good. Then we expect else, and then we're compiling the else branch. And that's it actually, right? So that's the whole thing. So this one should jump somewhere here. I need to save its address. How should I call that? Address what was that? Of condition, right? Address of condition, and it's basically the size of the body, right? It's basically the size of the body. So this is the address of the condition, because we'll have to backpatch it at some point. Afterwards, we also need an address of this jump, because we upfront don't know any of them, right? So we don't know any of them. So this is address of else, but it's not really address of else. It's an address of the thing that skips the else, not sleeps, but skips the else, right? So here is the address of the condition. We'll have to backpatch it, and the address that skips the else, we also have to backpatch it. So we'll have to go back to all of these things, right? So now we compile the body, right, so here is the compile of the else, and here is the interesting address, right? So address after else, we also basically taking it. Address after else. Can I just grab the whole thing in here? Just grab this whole thing in here. So now we have all the necessary things, I feel like. All of the necessary things, except we also need an address for the else. We also need an address for the else. So it's a little bit more complicated than while loop. It's a little bit more complicated than the while loop. So this is a jump if not, then the body, then skip the else address. So then the else itself, here is the address of the else. Here is the address of the else. And this is the address after else. Okay, that's pretty cool. So now we need to kind of stitch all of that stuff together somehow. We have to stitch all of that stuff together. Hopefully we'll be able to do that. Okay, so I do something like this. Function body items. And as far as I know, it's just a pointer, so we have to do something like add. So this is the address of the condition, right? So this is the address of the condition. And I just take that. So I dereference this whole thing, and now where do I jump, chat? Where do I jump? I jump to where the else begins, basically here. I jump here, like so. Okay, that's cool. So another one is address that skips the else. Address that skips the else. Can you see what I'm doing? No, you can't. Skip the else. So this one is after else. So that means we have to go here. That is basically it, I think. I have a feeling that is just it. It's a little bit messy, but I don't know how to organize it in a less messy way. What if I just like put all of them together like this? That didn't make it less messy, that's for sure. So by the way, since we're since it's a condition, I think I should just call it condition like this. So this is a condition. So arg and all of that stuff should become conditions too. So it's very important to organize this code visually so we can clearly see what's going on. For example, here is the if condition. Okay, so this is an address of condition jump. This is the address of the condition jump after we compile the whole condition. I feel like, yeah, this should be separated. Okay, and this is the sort of then body. So here is the then body. Okay, so at the end of the then body, we have a thing that skips the entire else, right? So because you fall into then, you reach the end of the else of the then, and so you have to skip the else. Okay, that makes sense, right? Then you have this else thingy. You have this else thingy. And then you take its address. It's very important because this is where you're going to be jumping if this becomes false. How do I visually organize this stuff? I have a feeling that the best way for me to organize this stuff is something like this, so you can clearly see that this is else. Here is the condition with the if. Here is like handling of the condition. Here is the then branch. Then we have else keyword, and this is the else branch. And then at the end, we stitch in all of these things together. So address condition jumps to address else right before the else. Address skip else jumps into after else. I think we stitched everything properly, more or less. We need to actually test all of that stuff. So first of all, let me try to compile this entire stuff. let me try to compile this now stuff. So mismatch type. I think at the end in here, it has to return sum, right? It has to return sum. All right. It worked right away. I was about, god freaking damn it, like I was about to create a small example that just like tries, like minimizes the complexity, but it just worked first try. Well, I mean, we need to test some things. Okay, so let's just go ahead and, for example, for the first element in here, right, so I can take the, oh my god, so something like base, I'm gonna dereference it and put 1 in here. Yeah, it just worked. So we just implemented the, you know, if else, right? We just implemented if else. Isn't that absolute coding, chat? Isn't that absolute coding? That is absolute coding, in fact. Look at that. Right, so yesu. So I might as well do some other things in here, right? So for example, plus 2 words, put 1 in here, right? So put 1 in here, might as well do something like this. Then Emacs, okay, so this is gonna be 4. Yeah, so plus 2, 1, 2. This is sus. Did I do a fucky walking? Look at that. This is 1, 0, 1, 2. It has to be here, shouldn't it? Sus. Truly sus. One thing, jump instead of jump not. What are you talking about? Jump instead of jump not. This is a condition. Bro, literally this is why I put a sub mod when I was trying to implement that. What are you talking about? This is a condition. Oh, okay. Okay, I'm sorry. Alright, just a second. Which one? Address condition. So skips else. Yeah, it's this one. All right, thank you. I mean, it's a very difficult mentally thing, so I need to focus. All right, so just saying. So there's no condition in here then. There's no condition. Aha, so that was the actual mistake. Ah, all right. So thank you so much. I'm sorry. Again, it's a little bit difficult to do this kind of thing, right? So I have to literally visualize it in my head, right? So this is a very difficult thing to visualize in my head. And people are trying to backseat at the same time. Okay, so that's pretty cool. That's pretty cool. So we've got this kind of thing. I actually would like to maybe have only one first word. And in fact, maybe let's put this like this, n minus 2. Right, do I have minus? I think I do in fact have minus in here. Yeah, so I want to put it somewhere here, like so. And now, let's actually put something like 20. Emacs. Look at that, I'm doing a rather complex things. So this is a rather complex code, isn't it? Look at that. So this feels like more or less proper programming language. And by the way, I think we even parse statements also correctly, which means I can do things like this. I think I should be able to do things like this. Yeah, I can do things like this. Right. So it's up to the parser to actually do all of that stuff properly. Okay. So we initialize that, and by the way, this specific state should produce the classical rule 110 triangle Sierpinski thingy, but I'm not sure if it's Sierpinski specifically, or is it? I don't quite remember. And here we may not, we don't even need to do this kind of thing. I feel like, yeah, we can just do something like that. All right, so no spacing is required. No spacing is required. This is just a single iteration, so that's totally fine. Now we have to organize the rule 110 thing. Rule 110. So usually when you have something like this, so we have a bunch of bits and stuff, we need to basically collect first two bits. I don't remember, do I have two separate boards or not for rule 110? Because I implemented it for porth. I might as well just like steal some ideas for porth. So they have porth in here. So porth. Okay. Porth. It was actually on GitLab. So then porth. While loop smiley face. For loop implemented. I don't think B had for loops. I think it doesn't have for loops. So there is a while. Yeah. So here are all of the possible statements. I think B originally didn't have for loops. So you only have while loops, unfortunately. So rule 110, let me see. Do we have two boards? So there is a row and there is a display. Okay. So we actually did all of that within a single row. Understandable. So, and we stored all of that back into the original row. Yeah, I think I'm starting to remember how I did that. Okay, so what I have to do, I have to start with it. All right, I have to start with it. Then I have to perform OR. Then this one is basically, well, this is just it. Then it plus word, one single word, which is do OR. But this entire thing, by the way, have to be shifted by one bit. So just shifted by one. And I feel like that is it effectively. That is basically it. So we'll need to implement this stuff. So let's put S. And there's a really weird bug somewhere in x86-64 is that if I allocate too many variables, it starts, what is it called? I forgot what is it called. It starts segfaulting. Yeah. So this is the state. Let's actually call it state. S state. All right. So here is the initialization of this entire stuff, and here is the initial state. Okay. So can I try to compile this whole thing? I wonder. So we need multiplication. We do have, in fact, multiplication. We'll need bit shift to the left, and we'll need OR. So this is the two things that we'll need in here. Can we implement them? Let me try to compile the whole thing. Right, so expected. Yeah, so we don't have bit OR. I think it's relatively easy to implement, chat. I think it is. So let's do binop. So let's do bit OR. Right. So bit OR, and what's the precedence of bit OR? Does anybody remember? Is it is probably higher than assignment, right? It is definitely higher than assignment, but it is lower than less, I suspect. Right, I'm gonna put the bit OR here for now, but does anybody remember the precedence of bit OR? Right, so where does it go? So basically, the higher the index, the higher the precedence, right? So that means this is the lowest possible precedence. Bit OR, I think, is definitely higher than any of the assignments, but I'm not sure how it is higher of any of these things. So I don't know. It's kind of difficult to say. I'm going to put it in here for now. In C, bit OR is the same as OR. And we don't even have OR in here. So, bit ops are executed before. Well, I mean, that's basically on par with everything we have in here. Yeah, so let's actually just like introduce this thing in here. And so now this one is just this bit OR. Okay. So bit plus. Binop bit OR. All right, so we allocate a temporary variable into which we're going to be storing this thing. So it also means we need to introduce a new, what is it called? Instruction for intermediate representation. So LHS, RHS. Let's literally call it bit or as well, right? So why not? And this is the new thing. So enum OP, and this one is just bit or. All right. So and eventually we're gonna have like a small virtual machine in here again. So so this one, this is ARM. So this is a GAS A Arch Linux. Okay. Bit or, we're not gonna implement that for ARM yet. Maybe at some point. This is gonna be to do. I'm gonna focus on x86-64. Okay, so x86-64 is this. So, and we'll need to implement it at some point. OP bit or index LHS RHS. Can I implement it right away? Like, I mean, isn't it just this? Chat. I think it's just this, right? So on x86-64, right? I can load them into the registers and then I can just take OR, and OR saves it into racks and we just save it back into temporary variable. I think that's it. So yeah. Okay, well, we'll see. So, and this is just the you know, the intermediate representation. Might as well just copy paste this kind of stuff. Add bit or. We got a lot of architectures in here. So this is JavaScript. This is JavaScript for the JavaScript. I think we're going to do that later, as usual. All right, cool. I would like to first test some of these things. So let me see. I'm gonna create like bit or b. So this is main. And we're gonna just have printf d. Let's OR together 1 and 2, which should be 3, because 1 in bits is 1, 2 is 1, 0. You OR them together, you get 3, right? Makes sense. Makes sense to everyone. So, and that's gonna be basically the checksum of all of that stuff. So let's do extern printf, and let's try to just build bit or. Okay, we can also take a look at the ASM, right? So here's the ASM. So move 1, 2 into racks and rbx, or and save it back into temporary variable, and then we can do print. So yeah, so now we have or operation here. So if we try to run it, it is in fact 3, so it works exactly as expected. Pretty cool, pretty cool. So as you can see, once you have this infrastructure of adding more different operations, it's actually pretty easy to add more operations, right? So just like add another one. You just need to know how to implement it in assembly. But all of the infrastructure is there. All of the infrastructure is there. So let's take a look at the point. So now it complains about this operation. So let's go ahead and add it. So B or S. So bnopt. So it's a shift left, all right? So as shell. So since we have this kind of prefix bit, well, I mean, you can't really have SHL that is not bit, but for the sake of consistency, maybe it makes sense to actually introduce it. Okay, who has the bigger precedence, shift or OR? So who knows? So, by the way, maybe the precedence referenced in the reference. Preference, precedent. Kind of difficult to tell what's the precedent. Shifting by boost to the, like, I kind of want shift to have higher precedence than OR to make it kind of easy to parse this kind of thing, but I'm not 100% sure if it's correct or not. So yeah, let's actually say that it's going to have a higher precedence than OR, at least for this specific case. All right. So isn't it a convenient table, by the way, chat? Don't you think? I think it's a pretty cool table. right? Where you can see precisely the precedence and you can just like move it around and it actually affects how all of that is parsed. I think it's pretty cool. I'm really proud of this table, by the way. I'm really proud of it. Anyways, it's a cool table. Thank you. Thank you. I also think so. Anyways, what do we have? So now we need to do bit shift L. Am I still this idea? Feel free to do so. Feel free to do so. Bit or it's a cool idea. A shell, boom. So that means we have to do OP. Okay, a shell. I'm not even sure if that's original of an idea, right? So it feels like maybe somebody also came up with that at some point. Right. Anyway, so here's arch and shell. And this is x86-64. All right, so this one should be also pretty easy to implement. So bit a shell, and I'm pretty sure that it's also a shell in, you know, x86-64, isn't it? I think it's straight up like the same thing. Damn. I wish like all of the operations was as easy as was easy to implement as this. Right, so just like every corresponding operation has an instruction. Oh, by the way, I remember that, like I heard it from somebody, that x86-64 was designed to be easy to compile to from higher level languages. And that's why it has such like weird operations like enter and leave. Right, so because they were useful for higher level languages. Right. Is that true? Like I kind of vaguely remember, right? That like they design it so it's easy to compile into x86-64 from Pascal, for instance, right? So Pascal is a very high-level language. So thank you so much for the subs. Needs fall. I hope I pronounced your nickname correctly. Thank you. Yeah, but anyway, we don't really use enter and leave, and I think enter and leave basically is a prologue and epilogue of the function. It just like prepares the stack and cleanups the stack and stuff like that, and nobody really uses them that often. I've seen some compilers using it, but not very often. Quite often people just like manage the stacks themselves with a lower level instructions. Okay, so what do we have in here? So this is IR. Okay, so bit or bit. All right, so I'm gonna take this kind of thing. So this is a JavaScript. This one is super easy. SHL, and yep, something went wrong, and this is because I forgot to actually associate this thing with a specific token, right? So we have to have, if the token is, I think this is not, yeah, so it's a 2-character token, so we can't use this thing anymore. We have to do something like clex, shift, okay, so it's literally shift left, and associate that with binop, shift, bit, shift left, like this. So now it should be able to parse all of that stuff. Okay, so this is not SHL, guys. So invalid operation. Wait, how do I do that then? If not like this, x86-64 shift left. So I suppose shift left maybe is immediate thing. So SHL, yeah. So SNT count destination. Oh, it's just dependent. Okay, so destination count, and count is an immediate thing, isn't it? Sus. So extended shift instruction. I don't like this page, by the way. So let me see. Where is the, yeah, this one. x86-64 and SHL. So without affecting flags. All right. So there is register memory 1 CL. Ooh, what is CL? CL times. Is that a register? Does anybody know? Is that a register? I'm not quite sure. What is CL? Operand CL. The destination operand can be a register or memory location. The count operand can be an immediate value or the CL register. The count is masked by 5 bits. Okay, so 2 to the power of 5, 32. You can only like shift by 32, which means we have to be a little bit more creative with how we generate a final assembly. x86, 64. Right, so we kind of loaded all of that into RBX, but we might have actually loaded RHS into RCX. Right. So, and because of that, yeah, so it's loaded into RCX, so it has a CL probably, and it should be able to shift this kind of thing. So which kind of weird. So that means it can only shift by like 32 bits, but what if I want more, like 64? Do I have to do 2 shifts? Is that something I have to do? So I want to test it out, chats. So shift.c. That's very interesting. So if I have x, actually let's make it 64-bit. stdint.h. So uint64x, and let's put 69 in there. So then I want to shift this entire thing by, let's say, 1. But I'm not sure, like it will probably use immediate, right? So definitely going to use immediate. 6-bit for 64, really? Does it use 6-bit? The count is max 5 bits. Freaking, I missed. I'm sorry, like my attention is kind of all over the place when I'm streaming, so I sometimes skip some of the things, but so it means it's totally fine for this stuff. Right, we don't need to test that. All right, so let me try to maybe run the whole thing. So, and yeah, so something went horribly wrong. So it definitely didn't work. Might as well take a look at the assembly. So SHL, yeah. So this is RCX. That's a lot of things. So we move. This was from the pointer. Look at that. That's a lot of intermediate variables in chat. And I have a feeling that, oh man, yeah. So that's I forgot about the temporary variables allocation, right, in the conditions and stuff like that. GMP, if, like, where is the if? Where is the if? So somewhere here. Yeah, so this is where we have to deallocate all of that stuff. So we are saving, before compiling the expression, we're saving this entire thing. Then we're testing the condition, and then after the condition, we are restoring the whole thing. Yeah, like this. I completely forgot about this stuff. So, and because of that, like we have, a huge amount of temporary variables. So this thing may allocate temporary variables, and then after checking the condition, we must allocate them. All right, so let's freaking go. Well, it didn't fix anything, but I hope that at least we don't have, well, we still have a lot of, yeah, so that didn't fix shit. Understandable. Well, oh yeah, because it's not about that even. So let's just maybe test this thing. So we have bit or. What if I rename this entire thing to just bit? Right, and this is where we can test some of these things. Mod simpc, and let's revert. So what do we want to test, chat? Let's just test shift by like 5. Right, 2 to the power of 5 should be 32. Right, if that is implemented correctly, that should be that essentially. Bit, let's fucking go, 32. So that operation works correctly. Cool. So that means somewhere in there, in the pointer, something is wrong because we're doing something wrong, right? That is absolutely understandable. So if okay, so we're just saving all of that stuff into the state. What if I comment out this entire thing? So this is the pointer. So it works. Then if I uncomment this thing, it doesn't work. What if I just save 69 into this state? Will that work? That works. What if I just save dereferenced it? Right, so we're trying to bisect the problem. We're trying to bisect the problem. So is it going to work? Okay, so we couldn't read shit from it. Well, because we never actually assigned anything to it. That explains it, because we're dereferencing 0. So we can do something like this, right? But I'm not sure. Maybe I will. So this is the initial sort of state before we go into the loop or anything like that. I think it makes sense to initialize it in here, right? So because then we're going to organize the loop to do all of this stuff. Okay, so we've done something like this, and that seems to be working, right? So it doesn't print anything because both of these things are 0, but that's totally fine. We can print this state because why not? 0. All right. So here we initialize the last word with 1. We can do something like this. So base plus 0 words is going to be 1. So the final state is going to be 1. Then we can take the next word and also put 1 in here, and that gives us 3. So then we can take another one. Well, I mean, that doesn't affect anything, right? So that everything is correct. So we have 2 first bits and they're 1. So that is totally fine. So if I remove this thing, we can clearly see. So this is 3. And what this thing did, it effectively took these 2 bits. It took these 2 bits and just put them together, and that is 3 effectively. That is effectively 3. So that is correct. That is correct. Cool. Very, very cool. So after that, I feel like what we have to do, we have to have I point maybe at 2, right? Because we had, 0, then 1. We should probably remove multiplication because we don't do any optimizations in here, right? So that's kind of important. So I'm programming like there's some optimizations, like all of that shit is going to be optimized out. This compiler doesn't optimize shit. So, but I still have all of these habits, right? Because of that, each multiplication in here is going to be performed as multiplication, right? So it's not going to remove all of that stuff. So you have to be careful in here. Anyways, so here we should start the loop, right? We should start iterating through all of this stuff while I is less than n, right? While I is less than n. So that's pretty cool. Okay. So, but maybe what we have to do is actually it plus so base plus 2. So this is the first 2 things, and then we start from 2. Which also means that we have to do state equal state to the left 1 bit, right? And then or the current bit that we have in here. Also makes me wonder, what if we had something like this, and then I can do maybe state. Yeah, I think the time has come to introduce these, assignment operations. That would be actually super cool. Yeah. I really like this style of developing a language, is that you try to implement a program that you want, and then as you encounter the need for certain features, you just implement those features. I really like that. I already talked about the style, right? So I use the style all the time, but like every time it works, it's just like very satisfying. Okay, so we got some stuff. B operator precedence from section 4.1. So 4.1. Primary expressions. So binding expression is the same order as the subsection shift operators. So in 5. Okay, so I don't know which reference you're using, honestly. Oh. What the fuck? Why there is no 4.5 specifically for the shift operators? Yeah, so it's the problem with OCR. All right, so I'll fix the precedence like later, right? So at some point. Thank you for the heads up. So it actually explains all of that stuff. This is a weird coincidence, isn't it? Right, it's a really weird coincidence. So anyways, let's introduce some operators. So binop. So assign plus. So we need both of these things, both variants of these things. So I'm going to call it assign bit or SHL. And all of them, I suppose, going to have the same precedence as the assignments, because that kind of makes sense to me. SHL. Well, what's cool about assignment operators is that they don't introduce a new intermediate representation, right? Because it's a combination of, well, whatever operation we have in here plus assign, right? You don't need more intermediate representation. That's what's cool about it. Okay, so now, so this is a shift left, so that means it has to be schleck. Yeah. Assign bit schleck. This one is yeah. So what is it called? I need to go to the Lexa, but I think maybe I can do stuff like this. Oric. It's called Oric, chat. Man, Sean Barrett actually came up with the funniest names for these things, like Shrek, Dick String. I don't know why it's funny, but I mean, Oric, Zorik. Okay, so where is the binop stuff? So, and in here, this one is Oric. Bit shift or. Shrek operator, yeah, Shrek operator is super cool. I do agree with that. So it has to be prefixed bin opa. Excuse me. Bin opa. Давай. So here is the assign plus, right? Assign plus. So that means we should have similar things for the rest of it. There's a lot of like copy-paste code. I'll probably have to compress that at some point. Get out of my swamp. I'm starting to get used to crust. Yeah, so crust is like very easy to get used to at some point. It's like if you don't really do too many things with pointers, right? It's kind of fine. All right, so what is that? Assign bit or, and it's just bit or. This is definitely something that could be compressed. I can actually feel it. You can definitely compress all that stuff. So this one is a shell, so that should be fine. And that's it. And it's loops. I think I know why. Because, yeah, because we never did +1 in here. Right, we never did +1. Okay, so we got the state. Right, so we got the state to particular state. And now I think we need to mask it out. Yeah, we definitely need to mask it out, otherwise it's not going to work. So we have to do something like 7. And if I remember correctly, 7 is this. Yeah, it is 7. So that's correct. So we want to do something like this. Can I maybe? Yeah. So that means more operations. That means more operations. But once you've got the state, you need to perform a lookup in the 110 table. Right, so 110. So this is a lookup. And you just use this as an index. You do shift right by the state, and you mask out 1. That's a lot of new operations, right? So we need to have shift left, shift right. And this is the basically new states, right? So this is a new state, which you actually save, believe it or not, to previous values. So it's going to be it -1 minus single word, right? You save it in here and just like assign it like this. Yeah. So you compute in the current state, you mask it out just in case, right? And then you just continue doing it. And that's basically it, I think, except you have to do also plus word. All right, something like this. Afterwards, what you have to do, you have to print this thing. So this is a single iteration, right? This is a single iteration. After that single iteration, you print the next state. Yeah, you print the next state. It's kind of difficult for me to factor out some of these things in here because we can't pass arguments to the functions. But it's not that big of a deal. We can copy paste for now. Right, so here's initialization, right? So here's the initialization of the board. We're printing the state, then we're computing the next state, and we're printing it again. So for now, I feel like I can maybe do exit 69, right? So here's printing the state, and for the exit, we'll need a function in here. Okay, so yeah, it doesn't like this kind of thing. So we'll need to implement that. Yeah, let's go ahead and do that. So though for now, we can implement it like this, right? Because we definitely need both of the operations, like ampersand equals and just ampersand. So let's actually start with the ampersand. All right. So it's kind of cool. Like Rule 1.1 always a very cool program because it allows us to implement like a bulk of different useful binary operations. So bin op. So bit end, and I think bit end should have a higher precedence than bit or. That kind of makes sense to me. I think it kind of makes sense to me. All right, so and now this one ampersand, it's bit end. What is rule 1.1? It's a cellular automaton. Rule 1.1. It's this one. So yeah, so you can check it out in here. It's a very simple cell, like a one-dimensional cellular automaton, and it's believed to be Turing complete. So it's similar to Conway's Game of Life, right? But in one dimension. So maybe yeah, it makes sense to actually put it in here. I've actually done a lot different streams where I implemented Rule 1.1 for different languages, for different systems. So nothing much to say about it, honestly. Nothing much to say. So bit or, so for this thing, I think it's very easy to just copy paste all of that stuff. So bit end, yeah, bit end. So enum op bit end, and we'll have to go through all of the things in assembly and just implement all of them. So this is end. All right. So x86-64 or should be also super easy because I'm pretty sure x86-64 just has end. So then bit or this one, yeah, very easy to copy paste. Keep making the same mistake. To do is the implementation is, oh yeah, so yeah, to do is like implement later. All right, when the program encounters to do during the execution, it will basically crash, telling you that you need to implement this kind of thing. Right, so that's what it does. Bit or, bit end. Why do I keep making this mistake? I don't know. All right. Very interesting. Yeah, so that worked out. That actually kind of worked out, which is interesting. So let me try. So some things in here. What if I have like this? This is 15. And if I go to bit B and I just try to print 15, it will be 15. But then if I do this 7, it should be 7. Yeah. So might as well do something interesting. So 0, 1, 0, right? So 21. Okay, so if I put 21 in here, right, 21, it is 21. But then I want to mask out 7, effectively masking out these 3 bits. So that means the result is going to be 5. And the result is in fact 5. Okay, so adding new operations actually becomes easier. Damn, that's super cool. That is super cool, super cool. So shift right. So what about shift right? Okay, guys. So bit SHL SHR, the same. Let's just copy paste things around. Right, and I suppose shift left, shift right should have the same precedence for now. So those that we have in here. So SHL, very easy to copy paste. Hopefully at some point I'll figure out a way to compress all of that stuff, because it's kind of annoying to keep track of, but maybe it's not that important. We'll see. All right, so what's that? Generate function. So this is arch, we don't need that. So shell, very easy, because I'm pretty sure x86-64 has share instruction, so it does have it. Then, so what is that? So this is intermediate representation, so let's just put that stuff in here. Secure. All right, what else? Okay, so this one is not needed. All right, that works. So let's go into the bit B, and I have something like 32. Let's shift it to the right. So that means the result of this entire thing has to be 16, obviously, right? So, and did I forget? Yeah, I forgot to associate this entire thing. All right, so Shrek or something. Where is the Shrek? Okay, so bit binop. Where is that stuff? Yeah, it's SHR. Let's go. 16. Okay, so just divide it by 2. Just divide it by 2. Cool. Where is my pointer example? So this is not a really pointer anymore. This is rule 110, but I mean, whatever. So we have that. So that should already work, by the way. So, except we don't have this kind of operation, but that should already work. So we have exit 69. So let's freaking go. So this is the pointer. All right, and it printed the first state. And then it exited with 69, exactly as we instructed. Okay, I'm gonna put 69 after we completed the next state, because I want to test whether this thing is gonna segfold or not. Just want to test whether it's segfold or not. Right. Okay, it didn't segfold. We can maybe put something like 34 in here to confirm that it actually updated. Okay, so it is 34. Let's try to print now the next state. Right, again, we're printing the state of the thing, computing the next state, and then printing it again. Will be kind of nice to factor it out to a separate function, but that will require passing arguments to the function. We can't really do that right now, but we will be able to do that in the future. All right, so it didn't really compute anything new, unfortunately. So nothing really changed. Cool. I wonder why. Base 2 words. Yeah, that is true. Thank you. That worked. That in fact worked. So now we want to repeat this thing several times, preferably like roughly n amount of times. So for that, can we allocate j? I remember there was a bug that you can't really allocate too many variables, but hopefully that is not going to be a problem. J equal to 0, right? So, and while j is less than n, we keep repeating this whole thing. And it's going to be something like this. All right. So we first initialize the field with just one cell. We print in its state, and then we keep, computing the next one and the next one and the next one. Okay. One thing it worked. One thing I forgot is j plus 1. So B is Turing complete apparently. Did you guys know? So thank you so much, Chandler, for Tiamat's question. Thank you. Thank you so much. Also, Darukozer, thank you. Really appreciate that. It's pretty cool. Absolute trading. So it actually does a little bit more. Maybe we should subtract 4 or something. Right, I want it to stop when it starts repeating itself or something. We can do something like -4, like this. And yeah, so let's stop it. And then I can now control like how big of the field it is. Yeah, so we can have maybe even 100. Who said we can't have 100? Let's go. Yeah. And it's that is really cool, honestly. Right, so the fact that it's like a toy implementation of an ancient language and it kind of works in a modern context using B runtime, that is very fucking cool. That is very fucking cool. I really like that. So, so that deserves to be in examples. You can't really compile that to ARM, but I'll work on that. What's the assembly looks like? Let's take a look at it. Pointer awesome. Yeah. Nothing special, to be honest. Nothing particularly special. It's pretty big, right? Because we copy pasted a function that prints everything. But I think once we implement parameters for the functions, it should be possible to actually, compress it a little bit. All right, so that's absolutely a poggers. So actually, I think we should do not -4, but more like -3, because I feel like one line is missing. Yeah, so the last line is kind of missing in here. Definitely. All right, so let me put that stuff into the examples. And this is obviously going to be rule 110. Actually, I only plan to implement pointers today, but rule 110 is also nice. Was SSA a thing you wanted to do eventually? I'm curious about that myself. Yes, I will do SSA eventually, right? So I think it's a good opportunity to implement that topic. Okay. Damn, that's so cool. Like now I don't have motivation to implement arrays, right? So because, well, I mean, I can implement an array syntax at some point to make it easier to do the pointer arithmetics, right? So because whatever we're doing right now in here is kind of an ass, don't you think? Right. So these kind of things, like what the fuck is that? It's just like, it's like, nah, bro. I want to be able to just do something like this. Yeah. So this is actually equivalent to this. Like we definitely need to be able to do this kind of stuff, right? But all of that for later sessions, Okay, let's actually commit everything. Right. So let's commit everything. So we have untracked files. Did I commit some weird shit? Yeah. And let me commit that. Implement dereferencing and rule 110 example. And I'm gonna push that right into the repo. Okay, so I guess that's it for today. Thanks everyone who's watching me right now. Really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Azozin. So love you. Mwah.